Welcome back to week 4 of vibrations. Here is another example. I got it out of this book right here. Whoops, come back to me. This guy right here. And so there's an example right in the very beginning, one of the very first examples. The single degree of freedom spring mass damper system statically deflects 1 millimeter due to a 100 Newton load. I think from that we can actually get the stiffness, right? So there's a clue. When it is given an initial displacement of 20 millimeters, it executes 7 oscillations in 1 second. So right here is 1 second. So the period would be 1/7, right? Because you have 7, and here's the 7 cycles, 1 second. We have ourselves a period. If we have ourselves that would be the damped period, then we'd have the damped frequency. So we have already know some things, some approaches, and it decreases to 1 millimeter in the next 3 cycles, right? So that confused me. In the next 3 cycles means the 10th cycle, right here, boom, it got down to 1 millimeter. So it's at x, call it 10, is equal to 1 millimeter. Didn't write that very well. Let's see. Let's write that bigger somehow. And let's change colors. We'll go back to the red. So right here, boom, is x10, and it's equal to 1 millimeter. Right. So we start out at 20, get to and then yeah. And then here. So there's some data. So determine, find the undamped natural frequency, the damping factor, and the damped natural frequency. Well, we could actually probably find the damped natural frequency like right away, I think. I don't see any problem with that. Okay, yeah, right away. So let me go to this other sheet right here because I wanted to look at the graph. So we have the damped natural. This is going to be 1/7, or 0.1429 seconds. And then omega d is going to be 2 pi divided by tau d. Right? So we just have 2 pi over 0.1429 seconds. So we have a 43.98. So that was actually the answer to the last part of the thing. Other information we got is that the force required to, I'll go delta x because del was not, I don't want to use the del because it's the log decrement in this section. So we have 100 newtons, and we decided, and it went down 1 millimeter. Right? Let me double check that. 100 newtons and 1 millimeter. So that's 0.001. And so you could do that in your head, but it's 100,000 newtons per meter. Well, that doesn't look like a newton at all. There you go. And okay, so there's other evidence. Okay, so we also, unrelated to the other stuff, we know that the log decrement is going to be 1 over n ln of x n minus 1 over xn. So it's really, this goes back to the previous example right up here, right, where we were supposed to show this is true right in there. So that's going to be 1 over 10 and natural log of 1 millimeter over 20 millimeters, right? Because we started out at 20, went down to 1 in 10 cycles. And this is an empirical way to get the damping. So that's it's kind of an important thing to try to make some of these vibration calculations seem real. All right, we've been using red for too long. Let's go to that baby blue. All right, so our damping factor, can be found from the log decrement with this equation, where we have 2 pi squared plus this squared. 0.2996. Boom. And 0.04762. And let's go to green, because we need more colors in this world. So because we know this is true, and we have the other things, we can go like the natural frequency is going to be the damped natural frequency divided by our 1 minus the square root of our damping factor squared. And so we come back up to, we got the top 43.98 divided by the square root of 1 minus 0.04762 squared, right, is going to be 44.03 radians per second. You'll see there's not a lot of difference between this and that, because we don't have very much damping going on. But we have solved for this damped natural frequency and the undamped natural frequency. And we might mean it to do it in hertz, but we would want to know. I would probably ask the question with being specific about whether I want it in radians per second. I might say circular, not the undamped natural circular natural frequency would be radians per second, or the or I just say I want it in hertz, and then I mean the you need to divide by 2 pi. And we want the damping factor right in here. Okay, so I guess we could say, I guess we already got it, right? Because we got the damping factor right here. So what I want people to do most of the time is to go answers when writing something, so I don't have to go searching through the thing. I guess they didn't make an ABC, but they did ask them in order, so it's nice to put these in order. And because there's such a small difference between these two, I'm not going to round off to 3 sig figs, because otherwise they would be identical to each other. They'd both be 44. And so I want to have some amount of observed difference, so I'm going to go ahead and put those as 4 sig figs in my answer. And I'll keep that as 4 sig figs. I did the other one too. And so here are the answers to the thing. Whoop, did I mess up? No, I didn't. I got it right. Okay. 43.98. Yeah, I messed up a little bit, didn't I? 98 radians per second. And box it. The end. Let's do another example. Are we seriously doing another example? Dang. I get ambitious sometimes. Maybe it's because I didn't like the Coulomb damping, so I did more of these. See you soon.